Right, hi everyone. So this is gonna be the video for chapter 8, lecture 2. So we're finishing the chapter. So if you guys remember last time, we were talking about quantum mechanics, right? And the quantum mechanical model of the atom. So we left off at atomic emission spectra, right? So these colors that are emitted by certain elements are due to their electronic states, and the electronic states can be um, roughly thought of as Bohr's model here. Illustrates it pretty well. So this Bohr's model explains it for the hydrogen atom. But of course, we can't directly observe the electron. So, it's really hard to do it for any other atom than hydrogen. However, it is a good model for us to just have a rough approximation of what's going on inside the atom. So Bohr did a really good job at explaining the four colors of the hydrogen emission spectrum. At the very center, you have the nucleus, right? So hydrogen has one proton. And he said you can think of these stationary states as these like kind of orbits around the nucleus where the electron can be. So the electron can't be in between the orbits, but it can be in these certain states. Now, when the electron is excited, meaning there's some source of energy, so a flame, right? And so you guys saw that in the flame test when we put these atoms in a fire, they emit the colors due to the electron absorbing that energy and being excited, right? That's excitations when it goes up into another energy level, but eventually it has to come back down, and that's called relaxation. So when the electron relaxes and goes down the energy level is when the emitted color is observed. So for the four bands of hydrogen, it was explained that the purple band is when the electron relaxes from the energy level 6 to energy level 2. So that's the visible series. Is the home state of the electron is 2. And then for the blue color, it's when it relaxes from 4 to 2, and the green is 5 to 2, and the green is from 4 to 2, and the red is 3 to 2. So it corresponds to the energy gap at which the electron falls, right? The further away it's falling from, then it's going to have a higher energy, right? So notice that's why purple is when it falls from 6 to 2. And if it's just falling from 3 to 2, that's, a short energy gap, right? It's a small energy gap. So therefore, low energy light. So that's why it emits red. Okay. So that's for the visible series, it's called the Balmer series. There are other series going on too that are invisible to us, right? We do see the four bands, but we don't see the ultraviolet series, for example. So the ultraviolet series is where the electron's home state is 1. So where it falls from a high energy state back down to 1. Okay. And then we also have the infrared series, which is when the electron falls back to n is equal to 3. So its home state there is 3. Okay? So for visible, it's 2, ultraviolet 1, and infrared is 3. And then Rydberg came along, and he was able to actually predict the wavelengths, aka the colors, right, of these emitted bands through what's called the Rydberg equation. And I like this form better, so let me write it down for you guys on the board. 1 over lambda. Okay, so 1 over wavelength is equal to R times 1 over NF squared minus 1 over NI squared, where you can think of NF as the final energy level and NI is the initial energy level. Okay, so let's say that if the electron is falling from 6 back down to 2, 6 is initial and 2 is final. Okay, and then the Rydberg's constant, you can, I think this is on your conversion sheet, but check. If it's not, you are allowed to have this. So R is going to be 1.096776 times 10 to the 7 inverse meter. And so yeah, that's a lot of digits, but you can also round to just 4 or 5 sig figs. You don't have to use the whole R. So let's do a problem where we use that equation. Okay. Oh, before we do that, so you can also, so the Rydberg's equation is predicting wavelength, but wavelength is related to energy, right? So if you were to transform the Rydberg's equation to the change in energy, then it would have this as the constant instead of R, right? So the form of the equation is very similar, right? 1 over nf squared minus 1 over ni squared. But just this constant is different because we are now thinking about it in terms of energy gap, whereas the Rydberg equation is solving for wavelength, right? And so they're related. So you just have to look at the problem. Is the problem asking for the change in energy, or is the problem asking for wavelength, right? If it's asking for wavelength, then use the Rydberg equation. If it's asking for change in energy, then you're going to use this equation here. Okay. So let's do this problem. A hydrogen atom absorbs a photon of UV light, and its electron enters the n is equal to 4 energy level. A, calculate the change in energy of the atom. So see, it tells you, right, the change in energy of the atom. So we're going to use the delta E equation, right? And then B, the wavelength of the photon. Okay, so we will be using this equation. I'll write that down. Delta E is equal to minus 2.18 times 10 to the minus 18 joules times 1 over nf squared minus 1 over ni squared. Okay. Okay, so reading the problem, right? It enters the n is equal to 4 energy level, and it absorbs photon of UV light. So we got to go back to the Bohr model. The UV series is n is equal to 1 is the home state. So now when it's absorbing from 1 to 4, 1 is initial, right? And 4 is final. Okay. So then I'm going to plug it in. One over 4 squared, because that's final, right? Minus 1 over 1 squared. Okay. Like that. Okay. So now we just evaluate. And I get 2.04 times 10 to the minus 18 joules. Okay, so 3 sig figs because of that number. Okay, so that's the answer for A, right? It's asking for a change in energy. And then in B, it asks us for the wavelength. Okay, so remember the energy equation. Einstein's energy equation. E is equal to hc over lambda. That's on your equation sheet, right? That's the equation that's going to relate for you wavelength to energy. So now you just have to solve for lambda. The lambda is going to be equal to hc over E. Okay, and we just solve for E, so all we have to do is just plug that in. Okay, so H, remember, is Planck's constant. That should be on your conversion sheet. It's 6.626 times 10 to the minus 34 joule times second. Okay, it's just a constant. It's the same every time. And then C, right, it's the speed of light. So 3.00 times 10 to the 8 meters per second. And then we're going to divide by energy. So our answer in part A, 2.04 times 10 to the minus 18 joules. So you can see how the units now work out. Joules cancels with joules, seconds with second. And so your lambda is going to be in meters. But I believe it asks for us to have it in nanometers. So we'll convert. Okay. So 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by 2.04 times 10 to the negative 18. So I get 9.74 times 10 to the negative 8. Yep, that's in meters. But it wants it in nanometers, right, guys? So we're going to do one conversion. 10 to the 9 nanometers. So 1 meter. Okay, so that's going to give us 97.4 nanometers. Okay. So if you guys orient yourself, where's 97.4 nanometers? So remember, red light is about 700, right? Purple light is 400. 97 nanometers is even shorter than violet. So that region is called ultraviolet, right? And sure enough, this is what the problem was asking, was for a photon of ultraviolet light, right? So that looks like a reasonable answer. Okay. All right, let's move on. Okay, so what we find out now, remember when we were talking about Einstein's photoelectric effect experiment, he found that light could behave like particles. So particles should also be able to behave similar to wave as well, right? There should be that duality. So Louis de Broglie, was the one that came up with the equation to describe the wave behavior of electrons, right? So electrons are normally thought of as small pieces of matter, right? But since there's a duality, these electrons can also have wave behavior, especially because the electrons are really, really small. So you can think of a wave length for an electron, right? Now, it's a little absurd to do that for a human, right? We are big pieces of matter. We also have a wavelength, but it's too small, right? However, electrons, being really, really tiny pieces of matter, actually has significant wave behavior. And so that can be described with this equation here. Lambda is equal to h over mv, where h is Planck's constant again. M is mass, right? And v is velocity. Okay. So then we can calculate the wavelength of an electron. So this problem says the electron's traveling at 2.65 times 10 to the 6 meters per second. What is the wavelength of an electron? Okay, so let's calculate that. So as you can see, that speed of the electron is fast, right? So as we were saying, things that are really tiny, they travel really fast. And so the electron is going to have an appreciable wavelength here. So let's calculate it. The wavelength of an electron is Planck's constant over mass times velocity. Right? So Planck's constant is 6.626 times 10 to the minus 34 joules times second. Divide by, we gotta look up the mass of the electron. This should be on your conversion sheet. Should list the mass of the electron, and you guys are gonna want to calculate it in kilograms. Okay, so look it up as kilograms. So it's 9.109 times 10 to the minus 31 kilograms. Okay, and remember how it works with joules, right? One joule is kilograms meters squared per second squared. So if we change that, kilograms meters squared per second squared times second, right? All I did was I substituted joules for this more expanded unit for a joule so that we can see how the units work out. Okay, and then velocity is given to us times 2.65 times 10 to the 6 meters per second. So you can see that kilograms cancel. Second here cancels with this second, and then this second cancels here. So we have all the seconds canceled, and then a meter squared over a meter squared divided by meters, meter. So great, we'll have the wavelength in meter. (2.74 times 10 to the minus 10 meters. Now let's put it into nanometers so we can kind of compare it to, you know, the other wavelengths of light. 10 to the 9th nanometer on top, 1 meter on bottom. So we're gonna have 0.274 nanometers as our answers for the wavelength of the electron. So it's small for sure, right? But it is actually in the realm of all the wavelengths of light, right? Which is really interesting because the electron was classically thought of as a particle, right? So it wasn't until quantum mechanics came along and kind of turned everything upside down and was like, actually, you know, light can have particle properties and particles can have light and wave properties. So here, what De Broglie has done was demonstrate that the electron had wave properties as well, okay? Which was mind-blowing, right, to the scientific community at the time, because that was not what we believed, right? But with this discovery, science and chemistry kind of took, you know, a major leap in advancement. And that's actually what affords all of the technology that you see here today. You know, our cars, our computers, atomic clock, iPhones, all of those things is because of this development, right? This discovery of quantum. Okay, so after that, there were other experiments that also proved that the electron had wave behavior. So another experiment was the electron diffraction. So remember when light was passed through a double slit, it would create this interference pattern. I remember waves would do that, but particles didn't, right? Particles would just produce two stripes, okay? When an electron was shot at this double slit, it also produced an interference pattern. So further proof that electrons can also have wave properties. Okay, so if electrons were to behave just like particles, there should only be two bright spots on the target. Okay. So let me show you guys a really cool video to explain further how the electron is behaving like both a particle and a wave.
Isn't really the way it is, and that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. We get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Particles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
All right. Okay. So from now on, right, we are going to imagine the electron not just as a particle, but also as a wave. It's actually both. Which is really weird, but it also makes chemistry really, really hard for that reason, right? Because we can't now observe the electron directly, because as soon as we even try to, it changes its behavior. Right? So what scientists have been able to do, what chemists have been able to do, is to indirectly observe the electron, and that's actually how we know all the things we know about it now. But there's still a lot more to know, right? There's there may be things that we can't ever know about the electron due to its dual nature. But so far we've done pretty good to be able to advance as far as we have in our society. Okay, so other experiments that show the electron was like a wave. diffraction patterns as well. So on the left side, you see that the X-ray diffraction on aluminum foil. So X-ray, of course, is a wave, right? And so it creates this diffraction pattern. Particles do not create diffraction patterns, right? And then electron on the right is the electron diffraction pattern, which looks very similar to the X-ray one, okay? Further proving that, yes, electron can behave like a wave. Okay, so as you saw in the video, right? Trying to observe the electron makes it change its behavior. So at its natural state, and just like the cat in the box, right? Before you open the box, cat's both dead and alive due to the radioactive particle being both emitting and not emitting radiation, because the radioactive particle is on the quantum level. The electron is also on the quantum level. It is both behaving like a particle and a wave. As soon as you try to like shine a light on it to figure out, its behavior, it collapses into one state only. So we can't directly observe the electron. And what we've seen is that because we can't, when you try to observe the wave nature of the electron, you cannot observe its particle nature and vice versa. And so what we call this is complementary properties. When you know more of one thing, you know less of the other. So the wave nature of the electron is due to the interference pattern. And the particle nature of the electron has to do with position. So what that means is the faster the electron, because the electron is traveling so fast, right? Only 100 times slower than the speed of light, we actually don't know its position exactly, right? The more we know of something, the less we know of the other. This is what we call Heisenberg's uncertainty principle. And it has this equation. Don't worry about all these symbols. So h over 4 pi, of course, is just a constant, right? Delta x is the uncertainty in position, delta v is the uncertainty in velocity, and m is mass. So since you have two things multiply each other to be equal to a constant, as you increase delta x, which means as you are, or as you lower delta x, which means you are more certain about the position, the velocity blows up. So you have a huge uncertainty in velocity. In other words, what we're saying is, we can't know the speed and the direction and the location of the electron at any given time. So the more you know about the position of the electron, the less you know about its speed and vice versa. Okay. And because this electron is traveling so fast, we don't know exactly where it is, right? And that gives us a conundrum, right? It presents us with a conundrum. Because how are we supposed to study the electron if we don't know exactly where it is? So the best way that we can describe where the electron is through probability only, since we don't know exactly where the electron is. Right? So that is the difference between classical physics and quantum physics. Classical trajectory in classical physics, you can think of as like the game of baseball, right? When a pitcher throws the baseball, the batter is actually quickly calculating the speed of the ball, the trajectory of the ball, right? At what angle is the pitcher throwing, and then predicting exactly where the ball is going to be so that he could hit it with his bat, right? So the key thing is, if the pitcher pitches the ball exactly the same every time, the ball should land in the same place every time, right? If he doesn't change anything about it, then classical physics says the ball should land at the same place every time, okay? Well, in quantum world, it's not like that. So now if the pitcher is pitching the electron, even if he's pitching the electron correctly, like pitching the electron the same every single time, sometimes the electron will be in the strike zone, probably most of the time, but sometimes it could be out of the strike zone, and sometimes in rare cases, the electron might even fly back at him, right? So it's just a probability in the quantum world. It's a probability of what's going to happen, right? It's not a determinate outcome. Okay? So what that means for us is we can guess, right? We can have an educated guess of where the electron is, but we don't know exactly where it is. All right, so in summary, right, classical physics, this is what we knew before. It was very black and white picture for us, right? We said matter is particulate, matter has mass, energy is a wave, and energy has no mass, right? But what quantum physics tells us now is that's not the truth. The truth is there's duality in everything, that matter can be non-particulate, matter can be wave-like, energy can be particulate and discontinuous, and energy also has mass. So in classical physics, right, light is a wave, an electron is matter. It's very black and white, right? But now we know it's not, right? We know that the electron is both a piece of matter and it can also be considered a wave at the same time. Right? Okay, so now that really gets us to the meat of this chapter, which is the quantum mechanical model of the atom. Remember, as chemists, our goal is to understand the atom so that we can understand the bigger pieces of matter. But what makes up the atom and what is really important when atoms bond are the electrons. So really, chemists are trying to understand the electrons, right, in order to understand the atom and bigger pieces of matter. Okay? But now the electron is so, we're so befuddled by the electron. It's doing weird things. How are we supposed to understand the electron? So the electron's position can only be known with some probability, okay? It can't be known absolutely. And the position of the electron has been solved for us through what's called the Schrodinger's wave equation. And this is very high level chemistry, so you guys don't really have to worry about that. You only have to worry about interpreting Schrodinger's wave equation solutions. So from his solution, we get this function that's called psi, and psi is called wave function. And the square of this wave function tells you the probability density of finding the electron inside the atom, right? So where most likely is the electron lying based on mathematics, right? Probability. So another note, Schrodinger's wave equation has only been solved for the hydrogen atom, because the hydrogen atom is it's the simplest, right? It only has one electron. But once you get to multiple electrons, helium, the Schrodinger's equation hasn't even been solved for that. We would need, supercomputers. We would need to have, a lot bigger computing power than we have now in order to do it. So what we've done is we've taken Schrodinger's wave equation solutions for the hydrogen atom, and we've kind of extrapolated to other atoms, right? So it becomes now approximations when you go to larger atoms with multi-electrons. All right, so what are you seeing here? In the top left picture is a snapshot of the electron, the one electron in the hydrogen atom. Okay, so if you can imagine, the electron's constantly moving, right, inside the atom. You're just taking snapshots, boom, 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 and then you overlay the snapshots on top of each other. What are you able to map out is where the electron spends most of its time. Okay, so that's our conundrum, right? Because the electron is in constant motion, we're like, where exactly is it? So we have to kind of do it in this way, right? Is to see where it spends its time mostly, right? Well, you can see that it's darkest towards the proton, right? Towards the nucleus, because the nucleus is positively charged and electrons are negatively charged, right? So the electron of hydrogen spends more time closer to the nucleus because it's attracted to it, right? And as you go away from the nucleus, you see that it's less dense, right? The electron probability is less dense. So the electron spends less time farther away from the nucleus. If you graph it, you can see that the probability density is decreasing as you increase the distance from the nucleus. That's to be expected, right? Now, sometimes what's better to measure is called the radial probability distribution. So you can measure that by putting like concentric circles around the nucleus, so it looks like an onion, right? And then you count the dots in each layer of the onion and you graph it. So again, when you see this graph, it's similar to the probability density, right? Except that there is a distance away from the nucleus where the electron spends a lot of its time, right? So that's the peak here, okay? And then it decays, right, as you go further away from the nucleus, right? So what we can generate then is a three-dimensional rendition of the electron density. So this is what you would see here. And it's called a 90% probability contour because, again, we're not completely certain where the electron is, right? And so to 90% certainty, the electron of hydrogen is going to be contained in the space, okay? And that's what we call an orbital. Okay, so you guys may have heard of that term before. So from now on, when I first learned about orbitals, I kind of freaked out because I was like, what is that, right? I've never heard of that before. But you guys, you don't need to, behave that way, because I'm going to explain to you very clearly what an orbital is. And it's actually really easy. It's just the probability of finding the electron in the three-dimensional space that's given to you. So here, this orbital is spherical, and you are likely to find, to 90% certainty, the electron lying in this sphere. Okay, so that's what the orbital is. All right, so the analogy for radial probability distribution is, you guys may have heard this phrase, right? Apple never falls far from the tree. So if you have, an apple tree and think of the trunk is where the nucleus is, the electron, being the apples, spends a lot of its time around the trunk, right? The apple drops from the tree, it will be closer to the trunk. And as you move away from the trunk, you're going to have fewer apples, right? So that's what a radial probability distribution is, except, we're talking about the electron and the nucleus, right? So if you were to graph it, you would have, again, a peak at some distance from the center, where you're most likely find the apples, right? Okay. All right, let's move on to the quantum numbers. So quantum numbers are the solutions to Schrodinger's equation. They're actually mathematical representations that we're going to use to understand what is going on in the atom. So a bit of terminology first. First, we're going to learn terminology, then the rules for the quantum numbers, and then we're going to take the quantum numbers and we're going to map it onto something that is real that we can imagine, right? So the principal quantum number is represented by n, and n can be any positive integer starting from 1. So 1, 2, 3, 4, 5. What does the principal quantum number represent? It represents the size of the orbital. So the larger the integer, the further away from the nucleus it is. So therefore, the size of the orbital gets larger. Right? And the second quantum number is called the angular momentum number. And that is represented with L. And this is a hierarchy, by the way. So L is going to be dependent on N. Okay. So notice what L can be. L can be 0 to N minus 1. So N will dictate what L is, right? So these quantum numbers, again, are hierarchical. So if N is 3, for example, then 3 minus 1 is 2. So L can be from 0, 1, 2. And that's it, right? And what does L represent? It represents the shape of the orbit. Shape, meaning what does it look like in 3D, right? It's the 3D 90% probability contour of that orbital. The third quantum number is called the magnetic quantum number and represented by M sub L. M sub L can take on values from minus L to plus L. So again, a hierarchy, right? ML would depend on L. And what does ML represent? It represents the orientation of the orbital around the XYZ Cartesian coordinate. And it'll also tell you the number of orbitals there are in a certain energy level. Okay, so let's do some examples so that you guys can see. Okay, at the very first level, right? That's the principal quantum number, n. So if n is equal to 1, then what can L be? Remember the allowed values for L is from 0 to n minus 1. So when n is 1, 1 minus 1 is 0. So L can only be 0. And then when L is equal to 0, ML can only take on values from minus L through 0 all the way to plus L. Well, if L is equal to 0, then ML can only be 0. Now let's go to n is equal to 2. N is equal to 2 means just a bigger orbital, right? And higher energy. If n is equal to 2, L can be 0 to n minus 1. So 2 minus 1 is 1. So L can be 0 and L can be 1. All right, next level. Beneath L is ML. And when you do ML, you need to do it for each L. So there are two L values here, 0 and 1. You have to do MLs for both, okay? So for L is equal to 0, ML can only be 0. For L is equal to 1, ML can be, remember, from minus L through 0 to plus L. So if L is 1, then start at minus 1. Go to 0, so minus 1, 0. And then the maximum is plus 1, right? So minus L through plus to plus L through 0. Okay, let's go to 3. When n is equal to 3, L can be 0, 1, 2. Why just 2? Because it's n minus 1, right? So 3 minus 1 is 2. So that's the maximum number of L. Then for each L, I'm going to list ML. For L is equal to 0, ML is 0. For L is equal to 1, ML is minus 1, 0, plus 1. For L is equal to 2, and you start at minus 2, right? Again, going through 0 and ending at plus 2. So for L is equal to 2, ML can be minus 2, minus 1, 0, plus 1, plus 2. All right, so again, what do these numbers mean? The first level is the energy and the size, right? How big the orbital is. And what's orbital again? The 3D region of space where you will most likely find the electron. So if n is larger, then you're going to have a larger region of space, okay? Then you go to L. L is shape, okay? So I'm going to show you all the shapes later the orbitals can take on, right, in this 3D space. And then the final quantum number, ML, gives you orientation. So how they're oriented differently in space, okay? So ML is the number that really tells you how many orbitals there are, right? Because the number of orientation is also the number of unique orbitals. All right, so if we count, guys, for n, when n is equal to 1, you have 1 maximum orbital. Okay? N is equal to 2, you can have 4 total orbitals, right? Because you have 4 ML values. For n is equal to 3, you have 9 orbitals total. Okay? So then if you count them all, if you sum them all up, 9 plus 4 plus 1, that's going to be 12. For 1, 2, and 3. Okay. What else you notice is the total number of orbitals is n squared. So when n is equal to 1, n squared is 1. So that's the total number of orbitals. When n is equal to 2, n squared is 4. So you have 4 total orbitals. When n is equal to 3, 3 squared is 9. Okay. So that's how it works. The total number of orbitals for a given n is n squared. Okay, let's do this problem together. Practice quantum numbers. What values of angular momentum, L, and magnetic, ML quantum numbers are allowed for the principal quantum number n of 4? And then it asks you how many orbitals are allowed for n is equal to 4. Okay. All right, let's go to the board. So for n is equal to 4, what can L be? Right? Remember, the rule for L is L can be from 0 to n minus 1. So what's 4 minus 1? 3. So that means L can go from 0, 1, 2, 3. right? So 0 to n minus 1. Okay? And then if you want to list ml, make sure that you do it for each L. So there are 4 values of L. So you have to do for L is equal to 0, you say ml is equal to 0. Right? And then for L is equal to 1, ml can be, remember, it's going to go minus L to plus L through 0, right? So minus 1, 0, plus 1. And then for L is equal to 2, ml is equal to minus 2, minus 1, 0, plus 1, and plus 2. For L is equal to 3, ml is minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. You guys see how that works, right? mLs can be from negative L to positive L, going up by 1 each time. So now, let's count the number of orbitals. This is 1. Here's 3, right? 1, 2, 3. So that's 3 orbitals. For L is equal to 1. For L is equal to 2, that's 5 orbitals. And then for L is equal to 3, that's 7 orbitals. If we count it up, that's 1 plus 3 plus 5 plus 7 is 16. Now, remember our rule? Total number of orbitals is n squared. N was 4, right? Okay, so you can see how that works, right? Why does n squared give you the total number of orbitals? We just showed it, right? So each one of ml value represents a unique orbital, right? And right now, you just have to know the numbers. But later on, we will map these to a shape. So that's easier to understand, right? But for now, each one of these is representing a unique orbital. Okay. All right, so now let's do it. We're going to try and map these numbers and make it mean something, right? So we already know that n means size. Okay, so because n means energy, right? The higher n is, the higher energy is. The higher the energy is, the farther it is away from the nucleus, and so therefore the larger the orbital, right? Pretty easy to conceptualize size, right? Now, L, also called a sublevel, is shape, okay? So n is level, L is sublevel, is shape. Shape tells you, the shape of the 3D space in which the electron can be. So the shape is designated by values of L. When the value of L is 0, we call that the S sublevel, and the S sublevel have a spherical shape. That's probably why it's named the S sublevel. For L is equal to 1, that's the P sublevel. The way I think about it is it looks like a peanut, right? And that's how I remember it. So it's the shape of a peanut, okay? But it's 3D, right? You can imagine that's 3D region of space where the electron can be, right? So the electron can't be here, it can't be here. It also can't be in the middle because that's where the nucleus is. But it can be here and it can be here, okay? Then when L is equal to 2, we call that the D sublevel. Okay? So D sublevel is like a double peanut. Again, that's how I remember it, right? Or 4-leaf clover, right? You can kind of see that. So the electron cannot be here, 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 but it can be in these 4 lobes, right? So that's what these are called. They're called lobes. So again, orbital means what? 3D region of space where the electron can probably be found, right? So L is just denoting what shape, right? What is that 3D region of space where the electron can be? And then when L is equal to 3, you have the F sublevel, okay? In this class, you guys only need to know SPD, the ones in red, okay? F is very complicated. I'm not even, I don't know about it, okay? So, so you guys don't have to, right? So you only have to know SPD. After L is equal to 3, L is equal to 4, just follows the alphabetical So after F would be G orbitals, right? And then L is equal to 5 would be H orbitals. Well, we don't need to worry about that because we haven't even found atoms, elements, or made elements that have utilized G orbitals, right? And so it's just theory right now, right? But we do have elements with S, P, D, and F. Okay. All right, so now to name these sublevels, first you put the size, and then followed by the letter designation of the sublevel. Okay. So for example, the 1s versus 2s. The 1 tells you that it's it's smaller than 2, right? S tells you the shape of it, so it's a sphere. So the 2s orbital is going to be larger than the 1s orbital. They're both the same shape, right? Because S is spherical. If you want to designate what n is equal to 1 and L is equal to 0, that's 1s, right? If you want to designate n is equal to 2 and L is equal to 1, that's a 2p sublevel, right? Because L is equal to 1 is p. The way I remember it is I just go S, P, D, F. 0, 1, 2, 3. And you'll just have to memorize that. Okay. All right. And then the ML. ML is the orientation. This tells you how many unique orbitals there are, right? So when L is equal to 0, ML can only be 0, so you only have one orientation. When L is 1, right, you can have 3 orientation because -1, 0, +1. When L is equal to 2, then you have -2, -1, 0, +1, +2. That's 5 orientations. Notice there's no even number, right? So what we can say is there are only one S orbital. There are 3 P orbitals, right? Because in the P sublevel, you have 3 orientations. Now, in the D sublevel, you have 5. So there are 5 D orbitals. 5D unique orbitals, okay? All right, let's practice designating the sublevels given N and L. So it says, give the name, magnetic quantum numbers, and number of orbitals for each sublevel with the following quantum numbers. All right, let me write this down on the board, and then we continue. All righty. So if N is equal to 3 and L is equal to 2, remember, off to the side, I'll just write S, P, D, F. Okay. That's L is equal to 0, 1, 2, 3. Okay, remember that, right? S, P, D, F, S, P, D, F, 0, 1, 2, 3. Right? So when N is equal to 3, L is 2, L is 2 is D sublevel. So this is a 3D sublevel. N is equal to 2, L is equal to 0, right? S, P, D, F, 0, 1, 2, 3. L is 0 is S sublevel. So that's a 2S sublevel. Okay, N is equal to 5, L is equal to 1. When L is equal to 1, it's a P sublevel, right? So this would be the 5D. And then N is equal to 4, L is equal to 3. When L is equal to 3, it's an F sublevel, and the size is 4. So you go 4F. Okay, so that's how you denote sublevels given N and L. And then it also wants us to give the magnetic quantum numbers, okay? And the number of orbitals for each level. Okay, so magnetic quantum number, when L is equal to 2, remember what ML can be? -2, -1, 0, +1, +2. So how many orbitals is that? Said 5. Okay. So the way you think of it is there are 5 orbitals in the 3D sublevel. let's do it for this one. L is 0. When L is equal to 0, ML is just 0. So how many values is that? It's just 1. So we only have one orbital in the 2s sublevel. Okay. Then here, when L is equal to 1, ML can be -1, 0, plus 1. That's 3 values. So yeah, 3 orbitals in the 5D sublevel. All right, the last one. When L is equal to 3, ML can be -3, -2, -1, 0, plus 1, plus 2, plus 3. Okay, that's 1, 2, 3, 4, 5, 6, 7. So there are 7 orbitals in the 4F sublevel. Okay. Okay, let's do this one. What are the NL and possible ML values for the 2P and 5F sublevel? 2P and 5F. We'll write that down. Okay, so I want NL and the number of orbitals. So N is obviously 2 here, right? Because that's a number in front, the size. L for P, remember the L designation for P that's associated with P is 1. Okay, and for L is equal to 1, ML can be -1, 0, plus 1. So that's 3 orbitals. Okay, let's do 5F. Obviously, 5 is the size, so N is equal to 5. And remember, F is associated with L of 3. Okay. And when L is equal to 3, ML can be -3, -2, -1, 0, plus 1, plus 2, plus 3. That's 7. Okay. So how do you think of it? There are 3 orbitals, 3 p-type orbitals, and there are 7 f-type orbitals. And it'll never change, right? That'll always be true. So it goes like this. There are 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. And that's always going to be true. Easy way to remember, right? It's just odd number. 1, 3, 5, 7. S, P, D, F. Okay? Okay, so now let's really go and visualize what these orbitals look like now that we know the quantum number. So we're going to start with L is equal to 0. And what is that sublevel, guys? It's the S sublevel. S stands for sphere, right? So the 3D region of space where you can find that electron is a ball, right? A sphere. So L is equal to 0. And we're going to take a look at inside, right? A cross section of these S orbitals to see what the difference is. So you actually have differences depending on what N is. Okay, so in a 1s orbital, you don't have any nodes, meaning you don't have any instance where you don't find the electron. The radial probability distribution is always positive, right? So there's obviously the electron is going to lie closer to the nucleus. So you see the shading is darker near the center, and there's going to be some distance from the nucleus where you most likely find the electron, right? So like right here. And as you move further away, it's going to decay. Okay. In the 2s orbital, which means it's further away from the nucleus now, right? And also bigger, you have 1 node. Okay. And what does that mean? The node is where you will not find the electron. There's 0% probability of finding the electron. So the way to imagine that is, just imagine the sphere, and then there's a shell inside where the electron cannot be. Okay. And then when you look at the 3s orbital, you actually find 2 nodes, 2 regions where you do not find the electron, where the probability of finding electron is 0. So if you look at the cutout, it'll be now 2 shells, right? There'll be 2 shells where you will not find the electron at all. Yeah. So you notice that the s orbital will have a pattern of n-1 nodes, right? So when n is 2, then you have 1 node. When n is 3, you have 2 nodes. And so when you have n is equal to 4, you'll have how many nodes? 3. All right, let's go to the next L number. Next L number is 1, and that's associated with which shape, guys? Peanut, right? So the p sublevel. Now, when L is equal to 1, ML can be -1, 0, +1, right? So you'll see that you have 3 p orbitals. Now, what do they look like? This is actually what they look like on the computer. So you see that instead of having a node, the p orbital has a whole nodal plane. So there's a whole, this plane right here that cuts through the nucleus, you will never find the electron there. So you only find the electron on the top lobe and the bottom lobe, but never in the middle, right? The whole plane. So it has a nodal plane, and the way to draw it is kind of just imagine like a figure 8, right? So I'll show you guys how to draw these orbitals later on the board. Okay, so remember, L is equal to 1 here. ML can be -1, 0, +1. That gives you the 3 orientations or the 3 unique p orbitals. Remember, the orientation means just how it's rotated on the XYZ coordinate. So if the peanut is lying on the x-axis, we call that the px orbital, okay? And it looks like this, right? If x is like this, y is this diagonal, and then z straight up and down, okay? So px, if the peanut lies on the diagonal, right, the y-axis, then we call that the py orbital, right? And then there's the pz orbital where the peanut lies on the z-axis. So 3 unique orbitals, right? And they're orientated differently. So again, what are we doing? We are just trying to communicate where the electron probably is, right? So it can lie like this, right? It can be in this or a region of space. It can be in this region of space. It can be in this region of space, right? If we're talking about the p sublevel. All right, next up, from L is equal to 1 is L is equal to 2. And that's the D sublevel. The D sublevel has 5 orientations, right? Because when L is equal to 2, ML can be -2, -1, 0, +1, +2. 4 out of the 5D orbitals have the double peanut, right? The 4-leaf clover. And then the 5th D orbital is kind of odd duckling out. It looks like a p orbital, that it has a peanut, but then it also has this belt, right? This is called the toroidal region, and it's like a donut in the center. So that's why this orbital is different than a PZ. It looks kind of like a PZ, right? But it's different due to that belt. Okay, so let's describe what the 5D orbitals are. You guys need to know this, and this will be on quiz number 4. All right, so the way that they're named is going to tell you where the lobes lie, on which plane the lobes lie. So notice, the DXZ orbital, the lobes lie in the XZ plane, right? This one here. The DYZ orbital, the lobes lie in the YZ plane. And then the DXY orbital, the lobes lie in the XY plane, right? You see that? Okay. And notice, these set of 3 are off axis, right? The lobes lie in between the axes. Okay? So that's how I remember them. I remember in sets of 3 and then a set of 2. So the set of 3 are where the lobes are in between the axes, okay? And then the 2 letters tell you what plane it is. The set of 2 are where the orbitals, where the lobes lie on the axis. So look at this one, the x squared minus y squared. The x and y tells you that the lobes lie in the xy plane, but that x squared minus y squared tells you that they are on axis, right? They're actually on the axis. And then the dz squared, that's the odd one out, right? Dz squared, the lobe lies in the z axis, and then the toroidal region or the belt lies in the xy plane, okay? And everybody's on the axis, right? So there you have it. That's the 5D orbitals. Okay, you guys should thank me now, okay? See what it says up here? Not tested. So if you go up one more and L is equal to 3, these are called the F orbitals. Again, this is the 3D region of space where you'd find the electron, probably, right? But like I said, I don't even know this. It's really complicated. These are all mathematical functions, right? These letters right here, right? Y cubed minus 3/5 YR squared are actually mathematical functions describing this shape here, right, of where the electron can be. Okay, all you need to know about F orbitals is that L is equal to 3, and there are 7 of them, right? Because of -3, -2, -1, 0, +1, +2, +3, right? There are just 7 of them, and that's it. You don't have to know how to draw them or what they look like. Okay? So at the end of the day, what you need to know, I'm going to show you what is on the next quiz. Is this. This is the last problem on quiz 4. Okay. So quiz 4, there are 4 problems. This one's worth 9 points, so one point for each orbital. I'll tell you guys what the rest of quiz 4 is, but this is one of them. This is the last problem. You'll have to know how to draw the s orbital, 3 p orbitals, and all 5 of the d orbitals. Total of 9. So for the s orbital, easy. Just draw a circle, right? Because it's a sphere. Px, py, and pz are easy as well. Just label for me the axis. Px will lie on the x-axis, right? Py, the peanut lies on the y-axis. And pz, the peanut lies on the z-axis. Okay, so show that to me so I know that you know what you're doing. Now with the d orbitals, the pictures I show you on the slide were in 3D. So drawing it in 3D is kind of tricky. If you are really good at that, like spatial reasoning, you can do that. I'm not that good, so I don't expect people to be. So you can draw your d orbitals in 2 dimensions. You just need to make sure that you label the axis clearly, so I know you know that a dxz orbital lies in the xz plane and is in between the axis. Okay, so that's how you draw the dxz in 2 dimensions. Then when you want to draw the dyz, right, just switch up your axis, y and z. Okay, make sure the lobes are in between the axis again. dxy, switch the labels, x and y. Make sure the orbitals are in between the x and y axis. And when you draw dx squared minus y squared, make sure the lobes are now on the axis. And then dz squared, the last one, just make, like a p orbital, and then draw a circle, just like that. So a tip for you guys in learning the d orbitals, because the first 4 is really easy, right? The s p orbitals are easy. The d, I would memorize the name first. So dxz, dyz, dxy. I would memorize the set of 3. This is off axis, right? Okay. Then the set of 2 is dx squared minus y squared and dz squared. This is on axis. Okay, that's how I would memorize it. And once I remember the names, then the name's going to help me draw the orbital. So I'm like, oh, let's draw the dxz orbital. Okay, so then what should my axis be? X and z. And the lobes has to be in between, right? And then, oh, what if I need to draw the dxy orbital? Then my axis should be x and y, labeled that way. And then my lobes should be, again, off axis, so in between. And then for the dx squared minus y squared, oh, okay, I need an x and a y axis again. But because it's dx squared minus y squared, I need to draw the lobes on axis. Okay. Yeah, so practice doing that. 9 points, right, on the next quiz. Okay, now the very last exercise we'll do for this chapter. We have 6 orbitals here, and you guys need to match the sublevel to their names, which are in the red box. But notice in the red box, there are 8 labels. That means 2 of the labels do not apply to the pictures here, right? Try and figure out which 2 do not apply, okay? So pause this video, assign the 6 orbitals, and then come back for the answer. Okay, so I'll tell you, right? A, obviously it's an s orbital, right, guys? Okay, so obviously an s orbital, in the box, I see a 2s or a 1s. So it's got to be a 2s because it's bigger than f. Right? So f is going to be 1s. Okay, cool. All right, when I go to B, obviously that shape is D. Okay, so I look in the box, I see three options. I see a 2D, a 3D, and a 4D. Okay. The answer for this is actually a D. And that makes D a 3D orbital. Okay. Now, you're going to be like, wait a minute, how do I know that that's 4D and this is 3D and not 3D and 2D? Right? Here's why. Let's look at whether 2D even exists. Okay? Because 2D means n is equal to 2. And when n is equal to 2, L can only be 0 and 1, which is an S sublevel and a P sublevel. Are there any D for n is equal to 2? Nope. So there's no such thing as a 2D orbital. Okay, tricky, right? Okay, let's go to C. C is obviously a peanut, and it's a smaller peanut. Inside the box, you have, again, three options: 1P, 2P, and 3P. C is going to be 2P, and E is going to be 3P. So you're like, wait a minute, how do you know that it's not 1P? Well, again, let's look at the rules. When n is equal to 1, L can only be 0, which means you can only have s orbitals. There's no such thing as a 1P. Okay, so there you have it. Okay, and that's the end of the chapter, guys. So go and practice, right? This chapter is not that hard as far as the math, but the quantum number can be a little tricky. So just practice, you'll get the hang of it, and then practice drawing your orbitals. Okay. I know the quantum numbers always gets people and it always needs clarification. So don't feel bad if you're like still confused on it. Allow me, come to office hours and allow me to just spend 5 minutes with you. And I promise you that I can, clear things up for you. All right. All right. I'll see you guys next time for chapter 9.